So now that you've been introduced to the concept of a mutex, and we've talked a little bit about mutual exclusion and critical sections, it's time to turn our attention to the structure and functionality of the Java ReentrantLock, which is the most common way of implementing mutexes in Java. So the Java ReentrantLock is part of the Java Util Concurrent Locks package, along with some other locks we'll talk about later, and it's used to provide mutual exclusion to concurrent Java programs. It implements the lock interface, which is also implemented by several other synchronizers in Java, and we'll talk more about those later. If you want to get a really good understanding of what a ReentrantLock does, I recommend you read the lock interface documentation, because it really explains what lock and unlock and try-lock and so on do. And then you'll see that the ReentrantLock class simply implements that interface in order to provide those semantics. Internally, a ReentrantLock is implemented by applying the gang of four bridge pattern. And essentially what this pattern does is it decouples an interface from its implementations, with the emphasis on plural, so that both fair and non-fair mutex semantics can be supported in a uniform way. And I'll talk in just a moment about what fair versus non-fair semantics are. If you take a look at this picture, this illustrates essentially the gang of four bridge pattern mapped onto the components that are in the ReentrantLock class. So you can see you have a ReentrantLock, and it's got a reference to something that's essentially the implementer class hierarchy, which turns out to be implemented by a base class called sync. And then we have both fair sync and non-fair sync. And those are going to be used to provide a common interface to different types of semantics, which is really what the bridge pattern is well known for. The locking itself is actually performed by this sync implementer hierarchy. And you can see sync is a class, and there's an instance of that class, also confusingly called sync. That's a field in the Java ReentrantLock class if you were to look at its implementation. The sync class itself actually extends the utility class that's part of Java Util Concurrent Locks called AbstractQueuedSynchronizer. And AbstractQueuedSynchronizer is a very powerful framework that is used by many Java synchronizers, including the semaphore and including the condition object. And basically what it does is it allows for FIFO, or first in, first out, wait queues that are used to queue up or park threads waiting to get exclusive access to some resource. And if you want to learn more about the AbstractQueuedSynchronizer framework, take a look at the link at the bottom of the page, written by my good friend and colleague, Doug Lee, who actually wrote the AbstractQueuedSynchronizer framework. And it gives a nice overview of what it does. Now, under the hood, again, within the implementation of ReentrantLock, the sync class is further extended to make two other subclasses, one called non-fair sync and the other called fair sync. And these allow support for essentially non-FIFO and FIFO semantics. We'll talk what that means in a second. But non-FIFO is the non-fair sync that basically is sometimes called haphazard, ability to let things go in whatever order the operating system and hardware deems most appropriate, whereas the fair version provides so-called FIFO semantics. And we'll talk more about that in just a second. If you want to look at the source code for all this fair sync and non-fair sync stuff, it's all available in the open source version of Java, which you can get by clicking at the link down below. The way in which the ReentrantLock selects between fair sync and non-fair sync semantics is based on a flag passed into its constructor. So one of the constructors for ReentrantLock takes a Boolean with a flag named fair. And as you might think when you look at the code here, if the Boolean is fair, then we make a new fair sync implementation. Otherwise, we make a new non-fair sync. And this allows selection between these different models when the object is created. This particular way of doing things is also applied by the Java semaphore class implementation, as well as by the reentrant read-write lock implementation. And so this is a good example of gang of four patterns being applied to very production quality, concurrent and synchronized software implementations. So it's a great example of the gang of four in practice. Fair sync ensures strict FIFO fairness. In other words, the thread that shows up first in line gets first access to the lock when it's available. And anybody who comes after, any threads that come after, they have to queue up in order. So it gives you fairness, but it turns out that there's actually a fairly non-trivial performance hit by doing fair queuing. In contrast, non-fair synchronization enables faster performance at the expense of fairness. So it's not necessarily fair, but it's likely to be faster. And depending on various factors, we might get a chance to implement fair semaphores in this course. And so you'll get a chance to see how how complicated they actually are under the hood and why there's extra overhead involved in getting those semantics. The default behavior of ReentrantLock, if you don't use the constructor that takes a parameter that's a Boolean, is to favor performance over fairness. So by default, it goes with non-fair sync semantics. As a general rule, fair sync is a lot slower than non-fair sync. So make sure you really need to use it before you set that particular policy. ReentrantLock has a lot of things in common with Java's synchronized keyword, which is part of the built-in MonitorLock. So the MonitorLock that comes out of the box with Java objects since day one has many things in common with the ReentrantLock. In particular, you can lock something to get exclusive access to a region of code, and then you can unlock it when you're done. So those parts are basically the same. However, there's also extended capabilities. So one of the capabilities you get is the ability to lock interruptibly, which means that if another thread wants to interrupt you, then the lock call will return after the interrupt request is set and sent to the thread that's in the lock. And by default, lock is not interruptible, but if you use lock interruptibly, then it is interruptible. And that's not a feature that you get with the synchronized keyword in Java. Likewise, there's also several non-blocking lock acquisition methods, two different variants of try lock. Very much like our spin lock implementation, try lock will check to see if the lock is available right away. And if so, it'll grab it. Otherwise, it fails. And the other version of try lock has a timeout, which will wait for a certain amount of time before giving up. In contrast, Java's synchronized methods and synchronized statements don't support interrupts. So once you've committed yourself to locking, you're stuck until you get the lock. And they also don't support any concept of non-blocking locking. So they're only blocking. So synchronized statements, synchronized methods are always blocking operations, and you can't interrupt them. So that's the end of the overview of the structure and functionality of Java ReentrantLock. The cool thing about the way in which many of the Java synchronizers are designed is they all use the same patterns. So once you understand ReentrantLock and its design, you have a pretty good understanding of Java Semaphore and its design. You have a pretty good understanding of Java ReentrantReadWriteLock and its design. Even though they do somewhat different things, they're organized and structured in a very similar way. And I find that very reassuring because it uses all these wonderful gang of four patterns that we talk about.